Hello and welcome to my CHEM1090 video blog. Calcium carbonate, or CaCO3 to use its chemical name, is present in a vast range of substances. It forms the basis of minerals such as limestone, marble, chalk, eggshells, seashells, and most importantly to me, coral reefs. Calcium carbonate is polymorphic, that is, it exists in more than one structure. Its three morphological states are vaterite, aragonite, and calcite. And as you can see, they are all quite different. Each one has different properties, and the ones I'll be focusing on today are aragonite and calcite, as these are the two most common forms found in nature, and the ones utilised in coral reef building. In particular, I'm going to focus on the relationship and interactions between CO2 and coral reef formation, as these are the properties of calcium carbonate that are of most importance and interest to me. Broken down, calcium carbonate contains two parts, the calcium and the carbonate. Firstly, it contains calcium, which is an alkaline earth metal. Carbonate is made up of carbon and oxygen, which are both nonmetals. In calcium carbonate, the calcium atom is a cation of 2+, and the carbonate is a non-polar covalently bonded anion of 2-. This results in a really strong attraction between the calcium cation and the carbonate anion. And as the calcium is a metal and the carbonate a non-metal, there is a huge difference in electronegativity, and so they bond to form an ionic molecule. The configuration of this molecule is as follows. It contains 1 atom of calcium, 1 atom of carbon, and 3 atoms of oxygen. As you can see, the carbonate is formed like so, and you can see the positive and negative charges of the two components, which then bond together like this to form calcium carbonate. As you can see here, these two forms of calcium carbonate are quite different. In calcite, it forms a hexagonal lattice, which leads it to have perfect cleavage along a rhombohedral crystallographic form. Aragonite will form an orthorhombic crystal lattice. Hard corals tend to utilise this form due to its strength. Another property that directly affects how calcium carbonate interacts with its environments is the presence of carbon dioxide. To form shells and skeletons, marine organisms such as mollusks, shellfish and corals usually utilise the bicarbonate ions and their own metabolisms to precipitate the calcium ions out of the seawater in this chemical process. Notice that this actually produces a molecule of CO2, but also notice it takes 2 CO2 molecules as input in the process. This is how coral reefs contribute to atmospheric carbon sequestration. Too much dissolved carbon dioxide in the ocean is predicted to have dire consequences for these organisms, as carbon dioxide will dissolve solid calcium carbonate. It does this by reacting with water and carbon dioxide to convert to calcium and bicarbonate ions. As calcium bicarbonate is soluble in water, this is a serious problem for organisms relying on calcified shells and skeletons.